So with this question, okay, the first thing I would do is make sure that my graph has a positive and a negative part to the y-axis, because there's going to be a part that where the person is moving in a negative direction, that is retracing their steps. Okay, so it doesn't have to be to scale, but I'm going to make the fastest speed right near the top, 25. Okay, this is meters per second. It's velocity. Okay, just so I've got all of that information on my graph. Okay, this is going to be time, but it's pretty hard to go back and forth between meters per second and minutes. So I'm just going to convert the seconds right off the bat, okay, into onto the y or x-axis. Sorry, so I've got that. So for the first, it says 10 minutes. The person drives at 25 meters per second. So I'm just going to kind of go out this way, and then right here at 10 minutes, which is 600 seconds, that's where it'll stop. Now, obviously, in the real world, there would be, you know, like they ran out of gas and they coasted to a stop, and then they had to get out of the car and do all that. We're just going to imagine that all of this stuff happens instantaneously. So the car runs out of gas, stops, they jump out, and they have the gas can in their hand, and they start walking. Obviously, that's not for real, but that's what we're going to say because it makes the graph easier to draw. Okay, so we drop right down to here, and now the person is walking for another 10 minutes. Okay, so another 600 seconds gets us to here, 1200 seconds. All right, at this point, the person stops and is standing next to the gas pump filling up the can with gas. So they are, where am I going to draw the next part of this line? Yeah, right along the x-axis, because they're not, their position isn't changing. Okay, and they have a velocity of 0. So they do that for the next 300 seconds. Okay, now here's the trick. I don't know how far it is from their car to the gas station. I know how fast they walked and I know how long it took them, but I don't know how far it is. And I need to know that because on the way back, they don't walk as fast. They're carrying a can full of gas, so they're a little slower. So what I need to know is how far is it from the gas station to the car. To do that, I'm just going to use this section here of the graph because it'll tell me that. I can just use the velocity, 5 meters per second, times the time, 600 seconds, and I'll know how far it is back to the car. All right, so we'll have our, was it 5? No, sorry, it was 1.5 meters per second. Okay, so 1.5 meters per second times, and we said it was 600 seconds. I can't believe I just typed that in. It's 900. Okay, so it's 900 meters back to the car. All right, now that I know that, and I know how fast they're going to walk back to the car, can I figure out how many seconds it will take them to get back to the car? Okay, so I'm just going to do a v equals d over t calculation here, where I'm solving for t. So t equals d over v, it's 900 meters, and divided by 1.2 meters per second. Actually, they're both negative, okay, because they're backwards. Not that that really matters a whole lot. Okay, so we're going to have 900 divided by 1.2, and it's going to take them 750 seconds, okay, to walk back instead of the 600 it took before. All right, so that means we're going to be at 2,200 seconds. Okay, over here. So now I'm going to draw down below and over here. Okay, a very common mistake, and I see this happen all the time, okay, is people, instead of drawing it over this way, they go like this. Okay, what is that person doing? They're walking backwards in time. Okay, they're not, and at a negative velocity and backwards in time. You can't do that. Okay, so obviously the graph, okay, should not look that way. Okay, so sorry, this was 1,500 and this was 1,200. Okay, so our graph should go this way. Once they get back to the car, we're going to say that they instantaneously got the gas inside, got it started, and started driving home, okay, at 25 meters per second. And of course, it would take them another 600 seconds to get home. So we would be at 2850, okay, for our seconds, and then they'd be back home. All right, so that's what our graph should look like for that question. Our velocity versus time graph should look that way. Now, the next thing that the car asked for is for a position versus time graph of this same movement. If I'm going to do that, I need to know how far did they go in each section of the graph. Now I already figured out that this one's 900 and so is this one. Okay, so I'm good there. I've already figured out those two. Okay, but I need to figure out this one and this one in order to be able to draw the entire position versus time graph. It's not hard. It's going to be 25 times 600 for both. Okay. All right, so when those ones there, they went 15,000 meters. Okay, now I can draw a position versus time graph for that data as well. Okay. Now, does my position versus time graph need a negative section? Am I ever displaced negatively from where I started in this question? Nope. I end up back where I started, but I never end up behind where I started in this question. So I don't need a negative part for my position versus time graph. Okay, so we start here at position 0 and we move at a constant velocity of 25 meters per second for 600 seconds. Okay, and that gets us to a position of 15,000 meters, right? And then we walk even slower, okay, well, we walk really slow for the next 600 seconds, right? And we go another 900 meters further. So I'm going to write 16,000 up here and then just be a little bit shy of that. Something like that. I know it's not really to scale, but okay. So then I get there, and now I'm at the gas station. I'm at the gas station for 300 seconds. During that time, I don't move. So I have horizontal line. Okay. Then I walk back to the car, okay, and that takes me to 2,250 seconds, just like it did up here. Okay. It's slightly slower than this one. So maybe something like that. Okay, it's a little bit longer. And then back home. Okay, so my position versus time graph, crudely drawn obviously, should look something like that. Okay, it shows where I went. It also shows that I got back to where I started. Okay, so I'm back at home, okay, after all of this is done. Right. Everybody all right with that? It's a very common thing to be asked, here's a velocity time graph, now draw what the position time graph would look like, because it makes you demonstrate a lot of different skills. It makes you demonstrate that you can interpret the velocity time graph and know what's going on. It makes you do some calculations, calculating displacement. Okay, in this case, also using V equals D over T to calculate some times. Okay, it allows you to demonstrate all of your skills essentially in one question. So it's a really good use of time on like a quiz or an exam because it shows me you can demonstrate everything without having to ask you 7 different questions. Okay, all right, everybody good with that one? Right. So I want to work on that a little bit more today, like some more of the graphing questions and V equals D over T questions. And then in the second half of class, going to talk about lab report expectations and things like that, because tomorrow we're going to do our first lab. Okay, so we need to kind of know what's expected there and how all of that's going to work. So we just did this question. We did this one yesterday. It's in a slightly different order on this worksheet here. Okay. But here's what we've got. You guys have done up to, I think you guys did up to question number 7. I think you did 8 as well. Okay, so what I want you guys to do here is 14 through 19. So you're working on page 3 and some of page 4 here, okay, in the workbook package. Again, in a couple of questions, it asks you to draw the graph. It doesn't have to be to scale, just a crudely drawn graph. Okay, will do the trick. Okay, so let's be working on those for now. And then, like I say, we'll go over any that give us trouble, and then we'll talk about lab report expectations and so on. Okay, so for number 14, okay, we want to plot a velocity versus time graph of all this motion. Everything's positive, so I don't need to worry about going into the negatives on my graph. Okay, and I'm going to plot this as quickly as I can. So we'll have all the way up to 8 seconds, right? So we got 0, 1, 2, 3, Okay, up to 8. All right, so in the first, and we go up to what, 20? So, all right, something like that. So at time 0, we have a velocity of 0 meters per second. So we start down at the origin. Okay, by time 1 second, we're moving at 4 meters per second. So we have this diagonal line representing the fact the object accelerated between 0 and 1 seconds. Okay, between 1 and 2 seconds, the object travels at a constant velocity of 4 meters per second. Okay, then between 2 and 3 seconds, it accelerates to 8 meters per second. And then between 3 and 4 seconds, it accelerates to 16 meters per second. Okay, and then between 4 and 5 seconds, it accelerates to 20, and then travels at 20 for the remainder of the trip. Okay, so we got to break this thing up into shapes that we can use. Okay, I'm just going to go like all the way across here and get a big rectangle there. Okay, have a small rectangle there. I don't know if everybody drew the same shapes as me, but those are the shapes I'm going to draw. Okay. But in the end, we'll end up with the same areas regardless of how we do this. All right. So determine the distance the car travels during the first 2 seconds. All right. So during the first 2 seconds, I've got this acceleration phase, okay, where my average velocity is actually half of 4. All right. So I'm going to go 4 times 1, which is 4, over 2 is 2. Okay. So this one is 2 here. And then I've got this rectangle that goes all the way from 1. Well, actually, I'm only trying to do it to 2 seconds here. So from this one here will be 4. All right. So in the first 2 seconds, it travels 6 meters. Everybody all right with that? Okay. How far does it travel in the first 4 seconds? All right. So then I've got to go to here. So I'm just going to erase this 4 and make this 12, okay, all the way across here. All right, so that rectangle there will be 12. Then I've got this small triangle that's 4 high and 1 second long. So it's the same as this one. It's only 2. Okay. Then I've got this rectangle here that will be 4. And then I've got this triangle that is 8 high by 1 long. So it's also going to be 4. So if I add those all together, I've got 14, 18. Okay. And another 8 is 20. Oh. Right beside the 12. No, I did the 12 all the way across. That's 1, 2, 3 times 4 is 12. I missed something. Did I forget one of the 2's? This is, oh, I did, yeah. Okay, 16, 20, yeah, 24. Sorry. Okay, so 24 meters there in the first 4 seconds. And then what distance does the car travel during the entire 8 seconds? Well, then we just calculate the rest of these shapes here. So we'll have this triangle here that'll be 2, this triangle here that will be, or this rectangle, sorry, here that goes from 4 to 16. Okay, so it's 12. Okay, and then we've got this one here that's 4 long by 1, 2, 3, 4, so it's 16. And then this box here that is 1, 2, 3 by 16. It's 48. Okay, so that should add up to 102. Okay, if we do it all right. Okay, any other questions on 14? All right, what other ones were we doing? Now I forget. 19? Okay. Okay, so for 19, we've got this object traveling at 8 meters per second north for 25 minutes. So this is a part 1 and part 2 question. Okay, so part 1, our velocity is 8 meters per second north, and the time I'm going to convert to seconds. So I'm just going to go 25 times 60, not times 6, so 1500. Okay, seconds, and then in part 2, okay, 5 meters per second south. for 15 minutes, which will convert to seconds. Okay, so that's 900. All right, now that I have those, if I want to calculate the average velocity, I have to remember that average velocity is total displacement over total time. Okay, I don't have the displacements, but they're not hard to find for each section. Okay, so D here will be 1500 times 8. Okay, is 12,000 meters. Okay, and then for this one here, 5 times 900 should be 4,500. Is that right? Okay, meters. That's south. This one's north, and it's important to realize that they're opposite, so I have to subtract them. Okay, so 12, I should have 7,500 meters south. Okay, divided by the total time, which is 2,400 seconds. Okay, and that should give me my 3.1 meters per second north. Okay. Any other questions on that one? Tom? Sorry, north. Yes, you're right. Okay. All right. And then what other ones are we doing? 14, 19, 20? Okay. So 20 is more a math trick than anything else. Okay. So it's not so much a physics question as it is a ratio kind of math-like question. It's not something I would that I would be likely to give you on a quiz or a test. All right. So what we have to think about here, guys, is one of the objects is going 1 meter per second faster than the other. That means that once they get moving, object B will gain 1 meter on object 2 every second. Agreed? Okay, because it's going 3 and object A is going 2 meters per second. So every second, object B is going to gain 1 meter on the first object. But the first object gets a 1 minute head start. So all I have to do is figure out how far it'll go in the first minute. That's how far it'll get ahead. Everyone follow me there? Okay, so if you're going 2 meters per second for 60 seconds, you're going to get a 120 meter head start. And now object B starts, and it gains 1 meter every second. How long does it take to catch it? Yeah, it takes 60 seconds. Okay, sorry, no, it doesn't. It takes 120 seconds because it's going to gain 1 meter every second, and it has to gain 120 meters. Right? So it's not really a V equals D over T question per se. It's more of a, I have to visualize this in my mind to kind of work it out kind of question. Okay. All right, let's talk about significant digits here now. Okay, so a couple things to write down. Okay, so the purpose of significant figures is this, or significant digits. The purpose is to not allow any mathematical operation to increase or decrease the accuracy of measured values. Okay, if I go out and I measure the track, okay, with a measuring tape that is accurate to the nearest millimeter, okay, when I get done measuring the track, I will find out that it is 400.000 meters. Okay, because I'm accurate to the nearest millimeter if I'm using a measuring tape. Okay, that means that any mathematical operation I do with that number has to reflect how accurately I measured that number. Okay, this number has 6 significant figures because I measured all 6 of the places that are shown in this number. All right, I wouldn't write this number like this. Because I don't know if that's a 0 or not. My measuring device was not this accurate. Okay? Therefore, if I do a bunch of mathematical operations, okay, I can't suddenly end up with this extra number on here because it would say that suddenly by doing math, I measured better, which I didn't do. Okay, so the whole purpose of significant digits is to maintain the accuracy of the measured values used in the calculation. All right. Now, in terms of significant digits, okay, what numbers are significant? The answers are all of them. If you measured them, they're significant. So any number 1 to 9 is a significant figure. 0 is sometimes a significant figure, because sometimes you measured it and sometimes it's just a placeholder. All right, so here's the weird thing about zeros. Okay, I call it zero significance. Okay, so okay, leading zeros. Okay, leading zeros would be something like this: 0.001. These are leading zeros. They are not significant. Okay, leading zeros are not significant. You don't measure them. Okay, you can't measure what is not there. All right, so if this was a measurement in millimeters, I have no meters, no decimeters, no centimeters. I didn't measure those because they're not there. Thus, they're not measured values. Thus, they're not significant. Everybody follow there? Okay. Trailing zeros. Okay, that would be like the one we just looked at, are significant. Always. Because I wouldn't write those zeros if I hadn't measured them. Okay, and then there are trapped zeros. That would be like 401.02. Those zeros are trapped. That means they were measured. Okay, they're not just holding a place, they were actually measured. Okay, so they are significant. Okay, doing math with significant figures. It depends on what kind of mathematical operation you're doing, okay, that it affects significant digits differently. Okay? If I'm adding or subtracting, okay, I have to go by the decimal places. Okay, I simply can't gain decimal places or gain accuracy by doing addition or subtraction. So if I am adding these two numbers together, let's say I've got 400.12 and I'm adding that to 1.173. Okay, how accurate can my answer be? 2 or 3 decimal places? 2. I can only be as accurate as the least accurate number I used. Okay, the least accurate number I used is only accurate to 2 decimal places. Okay, just because this one was measured better doesn't mean my answer can be as accurate as this. My answer can only be as accurate as the least accurate number. Okay, everybody follow? So my answer then would be 401.29. Okay, and that's it. That's as accurate as I could be. Okay, if you're multiplying or dividing, okay, you simply go by the lowest number of significant figures. Okay. not R, as. Okay, so if I'm multiplying 25 by 2, my answer can only have how many significant digits? 1. Because 2 only has one significant figure. Okay, so my answer can only have one significant figure. How do I write 50 with only one number? 50 should have two numbers, a 5 and a 0. Okay? The answer is I got to use scientific notation. Okay? Probably haven't used that since like the 8th grade, okay? But you have to use scientific notation in physics and chemistry a lot. Okay? So I would write this as 5 times 10 to the 1. Okay? That's 50 to one significant figure. Oh, sorry, I'm going too fast. Probably having trouble reading my horrible penmanship. This is why I usually pre-type all my notes. I know my penmanship is awful. It's always been awful. And they'll never get better. All right, so what do you need to know 99.9% of the time? Okay, because most of the time we don't do a problem that has only one calculation. Usually we like calculate one thing and then we use that to calculate something else and something else. Okay, you've got 2 or 3 steps to get to the end answer. If that's the case, write down your givens. Whatever your lowest number is, that's your answer's significant figures. Okay, that's what you're going to use 99% of the time, so it's really easy. Okay, what I usually have people do, okay, is just write down their givens. Okay, so let's say I had a question that gave me the following givens. Acceleration was 9.81 meters per second squared. Time was 4.1 seconds. VI was 2.319 meters per second, and I'm looking for VF. Okay, I would write down right beside the givens 2SD. So I know when I'm done, my answer has 2 significant digits. That will work for you 99.9% of the time. Okay, because 99.9% of the time you are going to have to do more than one operation, or you're only doing one operation and it's multiplication or division. Very rarely in physics do we ever just add or subtract two numbers. Okay, it's pretty rare. All right, that's significant digits. That's what you need to know to survive, okay, in physics 20, physics 30, chem 20, chem 30, okay, in terms of significant figures. But you're gonna have to use scientific notation a lot. Because there's no value to measure in a leading zero. Okay, so if we go back to the leading zero part here, and where I was talking about zeros, okay, this is, let's say this is meters, okay? This is less than a meter, right? I have no value here. I didn't measure any meters, so there's no measured value to be significant. Okay, same with decimeters and centimeters. I didn't measure anything there, so those can't be significant because I didn't measure anything, right? Whereas in this number here, okay, I measured numbers behind this zero, so I know that this, I measured this to actually be 0. Whereas here, I didn't have anything to measure. Yeah? All right, so that's what you need to know about significant digits. Okay, any questions on that?
Does the decimal place have any, I don't want to say does it have any
Effect?
effect on?
Only if you're adding or subtracting. Okay, if in this case here, this number has 2 significant figures. This number has 3. It doesn't matter where the decimal is. Okay, decimal only matters if I'm adding or subtracting. Yeah. All right. Any other questions? Okay. So we're going to be doing a lab tomorrow. Our electronic measurement devices operate on Bluetooth, so they will send the data to your phone, which is sweet. It's way better than having a measuring tape laid out on the floor and having to eyeball where carts and crap like that is, okay, at various points in time, which is next to impossible. And then you're getting very inaccurate measurements. So our lab materials or our lab equipment uses the kind of a Doppler effect kind of thing to measure how fast and where an object is. Okay, so when they're on, you can actually hear them popping a little bit. It's a very, very quiet popping sound. Okay, that popping sound reflects off of whatever it is we're measuring and comes back, and then the device can measure how fast it's going and where it is. But in order for that information to be sent to your phone, I need you to install this app. Yep. Okay. It's in the App Store, okay, or the Google Play Store, whichever kind of phone you have. Although, if you have an Android phone, we find that they don't work very well. For some reason, there's something off in the Android operating system that doesn't make it work very well. It's an Apple snob program, okay? So if you have an iPhone, go to the App Store, look up SparkView, get the free one, because there is a paid one, and you don't want that, okay? It's not worth paying for. Okay, we just want the free one. Okay, put the free one on your phone, and then tomorrow just make sure you're in a group with somebody who has a phone that has the SparkView app on it, and then they'll be able to email you all the data tomorrow, okay, and after the lab, and you'll be able to just graph everything in Google Sheets, and everything will work out really, really smooth. Okay, so if you have an iPhone, okay, then install the SparkView app, the free one, and we'll use it tomorrow to collect our data. Okay. Now, in terms of your lab report expectations, okay, I will be placing in the stream tomorrow the lab assignment, okay? So it is going to be submitted through Google Classroom to me. Right? I'm not going to get anything on paper from anybody, okay, for this assignment. It's just going to be electronic through Google Classroom, okay? The lab report will be in Google Docs, and you'll be using Google Sheets to build the graphs, okay? So I will put on there a template. Right? And the template will just be a blank document, okay, that'll have your name and then graphing lab or something like that is what it'll be called. Okay, you just fill in that sheet. Okay, so you fill in your problem, your hypothesis, your variables. Okay, it'll already be set up. It'll say manipulated variable, it'll be blank after it. You put it in and explain it. Okay, responding variable, you put in what the responding variable or variables are and explain them. Your controlled variables. Okay, the expectation is that you will always list 3 controlled variables, and I'll go over this again tomorrow. Okay, explain them all. And when I say explain, I mean this is a controlled variable because were it not controlled, it would have the following effect on the experiment, which would then affect the results. Okay. Then you'll have your hypothesis. Okay. And the hypothesis always contains if, and then. If this is true and this experiment is run, then this will be the results of the experiment. Okay. It's a prediction. Okay. It says what you think is causing the problem. It says what you're going to do briefly to test it and what your expected results are. Okay. A hypothesis always needs to say those 3 things. Then you'll have your the procedure. You don't have to write that out because I've already put it in the lab report template, so it's not something you need to copy. It's in there. Okay. You're just going to fill in your data, put in your graphs. Once you've built them in Google Sheets, you can just copy and paste them over. Then there'll be some analysis questions to answer, right? Now, on the analysis questions, you have a couple of options. You can try and type out everything in the analysis, including your calculations, which can get cumbersome, okay? Trying to find all the symbols and things like that that you need. It can be a bit of a pain in the neck. My suggestion is do it on paper and then snap a picture of your work with your phone. Okay, then you send that picture to your Google Drive, your @Isidore thing. Okay, send it there, and then you can insert it as a picture into your lab report, and I'll see it that way. Okay, so that's fine too. I don't mind if you do that. Put them in there, then you'll have your conclusion and your evaluation, so sources of error and things like that, and then you're done. Okay, you will be submitting that through Google Classroom. A couple of reminders about Google Classroom. The first reminder is Safari and Google Classroom do not play nicely with one another. Okay, so if you're doing this at home on an iPad, okay, or a Mac, make sure you have Google Chrome installed. and do everything through Google Chrome on those devices because Apple and Google don't get along. Okay, so you need to make sure you're in Google Chrome or some of the functionality is disabled, like the submit button or the turn in button. Okay, it's not there if you're in Safari, which can be a problem. Okay, as well as some of the other features, they don't work. Okay, so just make sure that you are in Google Chrome when you're doing this so that you don't run into problems. If you're having trouble or your computer crashes or whatever, okay, guys, we've got Chromebooks here. Come in and see me in scheduled help or at lunch. I'll give you a Chromebook and you can sit in here and get the work done, okay, that way. Or you can even do it on your phone, okay. I had like 3 students last year who did everything on their phone. I don't know how you type up a lab report like this. You must have much smaller thumbs than me, okay, but they were doing it and they did fine. But I would never do it that way because I'm a one-fingered texter, okay? Because I'm old, okay? I don't have like that dexterity that you guys have. So just keep that in mind, okay? That's how those labs are going to come in through Google Classroom, okay? Make sure that you have them done, okay? I'll put the due date in the stream when I post the assignment. The other thing that'll be posted with all labs and assignments is my instructions. Okay, so I'll record everything I tell you tomorrow. Okay, all the instructions. I'll record a demo of how to do the graph and how to import that in and how to export the data to all your group mates. I'll record all of that so that you have it all there. Okay, a really good idea when you think you're done your lab report is to go back over that recording and make sure you've done everything I said to do. Right? Because sometimes I add 1 or 2 little things in and people don't write them down and then they lose marks because they didn't do it. Okay, so just make sure you go over that again before you submit it. I will also post my data. Okay, because sometimes people aren't here, so they don't have the data. Okay, or maybe you look at your data and once you've built the graph, you're like, uh-oh, I did something really wrong. My data makes no sense whatsoever. Okay, in that case, you come and tell me, Mr. Codere, look, something went wrong. We don't know what. Okay, but our data is not right. And I'll say, then use mine. Okay, my data will be posted there. You can use it to confirm whether your data is close. You don't have to be exact, it's exactly the same as mine. As long as it's close or follows the same trend, you're good. But if you're, if we're all looking at a diagonal line and you're looking at, like a square, then you did something wrong and you need to use different data. Okay. Questions on the expectations for the lab report? It's pretty much the same as it was for Science 10. So just make sure you're ready to go for tomorrow. Okay. Having that app installed. Okay. So you're good to go.